So this lesson will start with the graphs of simple rational functions, a quick review, and then we'll go into the graphs of the reciprocal of a function. So let's start with simple rational functions. What I mean by that is functions of the form y equals k over x. And you may recall, we've done this a couple times now, that these end up being graphs that sort of look like this, where the x-axis and the y-axis are the horizontal and vertical asymptotes respectively. And if k is positive, well, that means that x and y have to both be positive at the same time, and then x and y have to both be negative at the same time, so that the equation would make sense. So you'd end up with a part of the graph in the first quadrant where they're both positive, and part of the graph in the third quadrant where they're both negative, and that's because positive equals positive or positive is the only way to make that work. Whereas if k is negative, then x and y have to be opposite signs, so positive equals negative over negative, for example, or negative equals negative over positive, and therefore you end up with regions in the second quadrant and the fourth quadrant. And of course, if you remember, these are called hyperbolas, and those are the asymptotes of the hyperbolas. So let's do an example. Find the axes, intercepts, equations of the asymptotes, and hence sketch the graph of f of x equals 3x minus 6 over x plus 2. Well, let's just start with the axes intercepts first. It's very easy to find the y-intercept. You just make x equal to 0. Basically, we're doing f of 0. I'm going to do it in my head. 0 minus 6 is negative 6. 0 plus 2 is 2. So negative 6 over 2 is negative 3. So we're talking about 0 comma negative 3. Now, to get the x-intercept, we would make y equal to 0. So 0 equals, and then 3x minus 6 over x plus 2. And so we solve that. Really, the numerator has to equal 0, so x is going to equal 2. And we verify that that doesn't conflict with the denominator, restrictions, domain restrictions, so x not equal to negative 2. So we're okay, x equals 2 is fine. So 2 comma 0 is the x-intercept. Now let's talk about the asymptotes. Well, I can find the vertical asymptote, x not equal to negative 2. So x equals 2 is a vertical asymptote, but I have no idea how to find the horizontal asymptote. And this doesn't look like a simple rational function, but I can make it look like a simple rational function by doing long division. So that's what I'm going to do. I'm going to divide 3x minus 6 divided by x plus 2. And so now I do x times y equals 3x. The answer is 3. Distribute that 3 back in. I get 3x plus 6. Now I subtract. Negative 6 minus 6 is going to be negative 12, and negative 12 is the remainder. So what we're really saying is that f of x equals, well, the answer was 3, plus, and the remainder is negative 12. So negative 12 is still being divided by x plus 2. So this graph got moved left 2 and up 3. And if you remember, the parent function here now is y equals negative 12 over x, which is that simple rational function, again with the translation going on. And the vertical and horizontal asymptotes on this one would have been the x and y axes. So if I move it left 2 and up 3, then that changes the fake origin, changes the fake axes. So the vertical asymptote, well, if negative 2, 3 is the fake origin, vertical asymptote is x equals negative 2, and the horizontal asymptote well, again, we moved up 3, so y equals 3. So I did long division on this problem. It was linear divided by linear, so that would make sense. And I ended up with a translation of my simple rational function. So now I'm ready to sketch. So let's start with the intercept. So 0, negative 3 is maybe right there. And 2, 0 is maybe right there. And now let's do the asymptotes. So x equals negative 2. And let's try to make it the same distance away. So label it x equals negative 2. Don't put a negative 2 here. You might get away with it, but you might not. And then, of course, y equals 3. And of course, you can put your open circle to the center if you want. Label this y equals 3. And now we basically know what to do because we know what the general shape of a parent like this is. In fact, we even have 2 points on here to tell us which quote-unquote quadrant. It's not really a quadrant anymore because we're dealing with the fake axes. But if I connect these, I kind of have a sense that it looks like this. And you can see the asymptotes. And then the other piece is going to have to be in this quote-unquote quadrant, this pretend quadrant, about the same distance away from the origin. So try to get some symmetry so it looks like this with your arrows, and then maybe extend these asymptotes a little bit further to get the general sense of what's going on. And now I've sketched and I've given all the information that I found, which are the axes, intercepts, and the asymptotes. So let's move on to another problem. Okay, so now we're moving on from simple rational functions, and we're now going to talk about the graph of the reciprocal of a function. What we mean by that is we have the graph of y equals g of x, let's say this one. We're now trying to sketch the graph of y equals 1 over g of x. So there's still that rational piece to it, but it's the reciprocal of a function. So the first thing I'm going to do is I'm going to draw my axes below the ones that I already have. Now I'm going to look at the features of the g of x graph. So first of all, I notice that I've got x-intercepts here and here. I've got a y-intercept here, and then this I'm going to assume is the lowest point on the graph. Maybe this is a parabola, maybe it isn't. I could at least say this is the minimum, but it may be the vertex. Okay, so if you think about y equals 1 over g of x, when g of x is equal to 0, in other words, when the y-coordinate is 0, the x-intercept, when I do 1 over g of x, well, that's undefined. So that will correspond to a vertical asymptote because I can't divide by 0. So let's put that in first. So there's going to be a vertical asymptote at x equals 2 and another vertical asymptote at x equals -6. And again, that's because when this graph has x-intercepts, when I do the reciprocal, when I do the 1 over y, essentially, I get undefined, and therefore I get a vertical asymptote. So those 2 points there corresponded to my vertical asymptotes here. Okay, the next thing I notice is that basically I'm taking 1 over the y-coordinate. So if this y-intercept is 0, -3, then the new y-intercept will be 0, -1/3. Now, I'm not going to be able to get exactly -1/3. I'm just going to eyeball it, but let's mark it over there as 0, -1/3. If I just say -1/3, that's probably sufficient. Also, this point here, -2, -4, well, the x is not changing. It's 1 over g of x, not 1 over x. And therefore, the -4 is the y that's changing. Well, when I take the reciprocal of -4, I get -1/4, which if you think about it, is closer to the x-axis than the -1/3 was. So there, right there, is the -2, -1/4 point. Okay, now let's think about what's going on near the asymptotes. So if let's start on this one. So I'm getting close to the asymptote over here. These y-coordinates are really, really small, but positive y-coordinates. When I do the reciprocal, I still get a positive, but now as these numbers get closer and closer to 0, these numbers get bigger and bigger and bigger and bigger from the positive direction. So this asymptote here must look something like this, where the y-coordinates are getting larger and larger and larger, but still positive. Now let's look from this side. Well, on this side, the y-coordinates are negative, but getting closer and closer and closer to 0. Again, 1 over a negative number, still a negative number, but 1 over a number that's very, very close to 0 becomes very, very large in the absolute value sense, so very, very negative. So on the asymptote from the right-hand side of x equals -6, the graph is doing this, getting very, very close to, or approaching -infinity. Do the same argument over here. These y-coordinates here are very small, negative, very close to the x-axis, slightly negative, and therefore the reciprocal is still negative, but going to be very, 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 very negative because these are almost 0. So 1 over something very tiny is going to be large in the absolute value sense, and therefore the asymptote to the left of x equals 2 goes down. And then on the right side of that, right here, these y-coordinates are positive but small, and therefore when I do the reciprocal, positive but large, and therefore the asymptote does this. Now there's one other thing I need to do, which is to realize that as these values get very, very large, as x goes to the right, these values get very, very large. When I do the reciprocal of that, those values get very, very small, still positive, Therefore, I'm going to have a horizontal asymptote on the x-axis. And the same thing's going to happen on this side. I'm going to have a horizontal asymptote on the x-axis. That's going to look like this, and then, of course, like that on the x-axis. Okay, so now I basically need to connect everything. So these get connected like this. These get connected like this. And then in between here, I get this thing where, oh, that's one more thing. This was the lowest possible value. So when I do the reciprocal, it ends up being the highest possible value, the highest possible value of the reciprocal. So that becomes the top of the graph. And then, of course, I have my y-intercept over there. And then it looks like that. And that generally becomes the shape of this graph. So again, x-intercepts of the original graph ended up becoming vertical asymptotes of the reciprocal graph. All the y-coordinates are flipping upside down, so taking reciprocal, so -3 becomes -1/3, -4 becomes -1/4, etc. Near those x-intercepts, you think about positives and negatives and how they're getting closer to 0, and therefore getting very far away from 0, again with the positives and negatives, the sign maintained. And any minimum here becomes a maximum, etc. So you have to sort of work out those key features. Let's do another one. Okay, we're given the graph of y equals f of x, and we want to sketch the graph of y equals 1 over f of x. Again, I've put axes down below it so I can match things up. First thing I notice is there's an x-intercept here at 1, 0. And of course, when I do the reciprocal of 0, I get a vertical asymptote. So there's a vertical asymptote here, and I label that vertical asymptote x equals 1. Then the other thing I notice is there's a vertical asymptote here at x equals 2, and that means that there was a dividing by 0 scenario in the y equals f of x graph, and therefore when I do the reciprocal, that 0 goes from the denominator back up to the numerator. So that vertical asymptote over here is now going to turn into an x-intercept on my reciprocal graph. So that x-intercept is going to be at 2. Okay, the next thing I notice is there is a horizontal asymptote here at y equals 3, so that when I take the reciprocal of y equals 3, I get y equals 1/3, and so there's going to be a horizontal asymptote here now at y equals 1/3. Now, I could try to make these scales match, but I'm not going to stress too much over it. So the fact that y equals 1/3 looks like it's just as far out as x equals 1. No worries. This is a sketch, not a careful graph. If I had a grid and I wanted to do a careful graph, then I would have to be a little more careful about my coordinates. Okay. The other thing is this y-intercept of 0, 3/2. When I do the reciprocal of that, that becomes 0, 2/3. Well, here's 1/3, so 2/3 is bigger than that. So the y-intercept now is over there, and I'm going to label it 2/3, the reciprocal of 3/2. Okay, so now let's talk about sketching all of this. So the first thing is, let's talk about the values near this x-intercept, which makes this vertical asymptote here. So these values here to the left are positive but very, very small. So the values to the left of this vertical asymptote will be positive and very, very large. So we're talking about going like this towards that asymptote. On the right-hand side of that x-intercept there, these values are negative but very, very close to 0. So when I do the reciprocal, these values will be negative and very far away from 0. So the asymptote's doing something like this. Now if I talk about, let's say, on the horizontal asymptote, let's look at these numbers. These numbers are positive, but they're less than 3. So when I do the reciprocal of something that is less than 3, it ends up being more than 1/3 because the denominator now is less than 3. So these values are going to be above that other horizontal asymptote. And then similarly, when I look at this side, these values here on the right side of this horizontal asymptote are higher than 3, bigger than 3. So when I take the reciprocal, it becomes something 1 over something bigger than 3. So that number becomes less than 1/3, and therefore the horizontal asymptote on this side is below the y equals 1/3. And at this point, I can start to connect these and get my graph, curve it, of course, to look something like this. And again, this is a sketch, so the fact that it's not perfect is okay. And that's all I needed. I got all the information that I needed, and I sketched the graph of y equals 1 over f of x with all of the relevant information included. So briefly, I want to talk about invariant points. So let's say this is the graph of y equals f of x, and it includes these 3 points, negative 2, 1, 2, 1, and 0, negative 1, which I've just labeled as negative 1. When I do 1 over f of x, I'm doing 1 over each of those y values. Well, 1 over 1 is still 1, so 2, 1 will still be on this new graph. 1 over negative 1 is also negative 1, so 0, negative 1 is still on the new graph. And 1 over 1 here is also 1. So these 3 points are exactly in the same location as they were before. In other words, they did not vary, so they are known as invariant points. So here where I superimpose the y equals f of x over the y equals 1 over f of x graph, you can see that those 3 points are in common. And again, the key here is that if the y-coordinate's either 1 or negative 1, when you do the reciprocal of either 1 or negative 1, you're going to get 1 or negative 1 back. So anywhere where the y equals 1 or the y equals negative 1, those points are going to reoccur on the reciprocal graph from the original graph. And the vocabulary we use is invariant points. And that's the end of the lesson.